So let's call them like we need names for them.
The dumb method in the calculus.
U substitution is where we're using the U. And then
Ben substitution. Ben substitution. Ben substitution.
the other one.
Well, technically we have three.
Alright, so let's look at number one. First thing I would do is rewrite it because there's not like a quotient rule for integrals. So if you have a fraction, you want to get it so it's not a fraction. So think about what you're doing when you do that. This negative goes with the 2, so that's negative 2. This right here is x to the first, so that's going to go up and become x to the negative first. And then this is also to the first, so that goes up and becomes like that chunk to the negative first. Let me do U substitution first, and then we'll talk through the other one too. So, what's the big guy in this scenario? This negative one, right? Because that's what's like that's what is impacting this. So that makes this your big and this your little. And what we're hoping for is this is the derivative of our little. Because remember what happens to the derivative of our little? It just disappears. So I'm going to set U. So this is my big. This is my little. So U equals negative 3 plus ln of x. So I take the derivative of this. I keep writing mu's because that's what it is in stats. Mu like mean, or I think it's also the coefficient of friction, yeah. So du over dx, so the derivative of this equation, working with x values, what's the derivative of negative 3? 0, and the derivative of ln of x? 1 over x. Or if I'm thinking about it in terms of this problem, isn't that also x to the negative first? Those are the same. And then multiply both sides by dx. So we get du equals x to the negative 1 times dx. Well, I'm almost matched up with the original problem, but I'm not quite. So, like I know I can put a u in place of this, but I've got 2x to the negative 1 times dx that I need to match up with. Right now I've only got x to the negative 1 times dx. So what do I need to put right here? 2. So if I multiply the right hand side, I'm going to multiply the left hand side. And now I know that 2 du is equal to 2x to the negative 1 times dx. Would it what? Oh yeah, that would be negative 2, wouldn't it? My bad, negative. It's negative because this is negative. Yeah. We good? Okay. So when I go to rewrite it, instead of those two things, what am I putting? Negative 2 times du, and I'm going to put the du like at the end. Instead of this, what am I putting? U to the negative first. The colors. You know what I mean. Now you understand? Okay. So, now my job is to integrate this. So, this is kind of where you either memorize it or you get stuck. I'm going to add 1 to the power. That's 0. I'm going to multiply by the reciprocal of 0. Oh, wait, that doesn't make any sense. Which reminds me, when I integrate a negative first power, what do I get? What was that? ln. So the integral of a negative first power, the negative 2 is just going to drop down. You have a natural log of absolute value of mu, u, plus c. So the derivative of natural log is u to the negative first. The integral of u to the negative first is natural log of u. You need absolute value signs because you can't take the natural log of a negative number. So we have to force it to be positive. And then I just plug back in negative 3 plus ln x in place of So I'm gonna do it again. That's the answer. I'm gonna do it again. Like talking through the other way. But question though that you have to leave the absolute value. Because you can't take the natural log of a negative, so we kinda have to force it to be positive. Question on this one, yeah. What do you mean get around?
Because like you said, if you add 1 to the power, it becomes 0, and 1 over 0 is 1.
Yeah, so you can't use the power rule for negative first powers. It's just a definition. If I'm integrating x to the negative first, it's the natural log of x. Because when we were doing derivatives, what's the derivative of natural log of x? It was 1 over x, so we're just doing it back. I only brought up the power rule because a lot of people see the power and just start doing it. I'm gonna add 1, I'm gonna add multiply by the reciprocal, but you can't do it in this case, and it's kind of fortunate that it doesn't work out because it's a good reminder that you can't do it in this case. Or what will? Yeah, if it's any other power in the world, you can do it. Just not negative 1. Yeah, if it was like negative 2, you'd add 1 and get negative 1. Multiply by the reciprocal of negative 1, and you'd be totally fine. Alright, let me talk through it using like the. I don't know what to call it. The big guy, little guy method, I guess. So it's the same concept. I need to identify like, okay, that's my big guy. That's my little. And then this needs to be little guy prime. So it's like, is it right now? I don't know, let's find out. So a lot of people, even if they're doing this method, will go off to the side and be like, well, there's L. So L prime would be 1 over x, or x to the negative first. Like, isn't this really just kind of doing a u substitution thing? Just doing with L's instead. And then you would just match it up a little differently. Instead of doing the u, some people will go, okay, well, that's supposed to be an x to the negative first. It's not. So 2 ways I can fix that actually. I could just yank that negative 2 out in front. Or I can multiply the inside by negative 1/2, because what's negative 1/2 times negative 2? It's 1, and what's the coefficient that we have here? Is 1. But if I multiply the inside by negative 1/2, I have to balance that out by multiplying the outside by negative 2. So you see how it's the same as if you had taken out a negative 2. Like that's what you were saying yesterday. You just gotta take it out. I don't know if that makes sense. At least that's now or not. Then little guy prime disappears. You add 1 to the power, multiply by the rest. Oh wait, that's not going to work because I got a negative 1 there. So the integral is natural log. This negative 2 drops down. And then I got a plus c. Is that easier? I mean, so like, yeah, it depends on, like everyone's brain's kind of different. Some people like that, use my process, I just want to go through this process every time. Some people like to, this is shorter, I don't know if it's easier. Question on that one? Either method? Yeah, I'm gonna keep going. Let's do 2. Well, yeah, you do 2. How do you say? Yeah, we do. It would probably be good to try it both ways. Give yourself an idea of like which one makes more sense to you. So that'd be my rewrite. So make sure you're starting there. this is my big guy. This is my little guy. So my little guy is 1 plus ln of 2x. So my little guy prime, what's the derivative of 1? I think I know where a lot of people probably messed up. Was the last one just ln of x? Yeah, okay. So ln of 2x is chain rule. So what's the derivative of ln of something? 1 over the something. You left out. And then you multiply by the derivative of 2x. What's the derivative of 2x? 2. But those cancel. So it ends up being x to the negative first. But did you just put 1 over 2x? Is that why? So you guys in chain rule. But if you ignored it, you actually ended up in the right spot. So. But do you see why? Do you see what you shouldn't ignore? Good? Okay. So this is supposed to be x to the negative first. It's not. It's 5x to the negative first. Well, I can fix that real easy. That 5's out there now. So now I have this integral where this is my big guy, this is my little guy, this is my little guy prime, and it's all good to go. Everything's fine. So once I'm all set up the right way, little guy prime is going to vanish. And then my big guy is a power. So my job is to integrate the big guy. Typically when I integrate a power, I add 1 and multiply by the reciprocal. Unless it's a negative first power. Then I do natural log. And then this 5 comes down with it. Here or here? Here? So just like the derivative of this? Yeah, okay, so L prime. Whoa, that's aggressively. Alright. So what's the derivative of 1? 0. So that doesn't matter. Then the derivative of natural log of something is 1 over the something. But then you gotta multiply by the derivative of the something. It's a chain rule. So what's the derivative of 2x? 2. So then that 2 and that 2 cancel, and you actually just end up with 1 over x. Or x to the negative first. You just did it so fast in your head you didn't realize. Does that help that you're asking? What if it's not 1? I'm gonna need a little more. I'm not trying to ignore your question, I just don't think you can hear that. Grandma, I'd like me to go through this with the U substitution. We're good? Okay. I mean, I'll do some of each. So let's try number 3. I think it's an E one, right? Or no, alright. I'll do, it's not from yesterday though. It's a trick. Because the big guy's a negative first power. So let's do this with U substitution. I'm going to do it this way. You can do your own method. So U, not mu, equals 4x to the 4th plus 5. The derivative of U with respect to x is 16x to the 3rd. So du equals 16x to the 3rd times dx. Well, I don't have 16x to the 3rd up there. I have 80x to the 3rd. So I can make this into an 80x to the 3rd by multiplying it by 5. Which would give me that 5 du equals 80x to the 3rd times dx. And then I can rewrite my integral in terms of u's. So 80x to the 3rd times dx is 5 du. This piece is just u to the negative first. And then my job is to integrate this. So I integrate the negative first power. So that's the natural log of u. 5 drops. There's your plus c. And then we just put it back. So this is more of a like, I do A and then B and then C and then D and then E and I get my A. A little bit longer, but it's less like thinking, I guess. it's shorter, but it could be easier to screw up if you're doing some of the stuff that you had. Yeah. It disappears. So that's the same as if I had like x squared times dx and we integrated it and we just said it's 1/3 x to the third. Like that dx disappeared too, right? We haven't talked about, do you want to know what it means? Like what it actually is? It's what you're doing. This is more than you bargained for. Your question's more than you thought you were getting into. So this is y equals x squared, let's say. There are a bunch of rectangles in here that we're using to estimate the area. What's the height of any one of those rectangles? If this is my x value, what's the height of it? Y, which I can also say is x squared, couldn't I? So if this is x, isn't this x squared units high? Like it's x comma y, but since y equals x squared, it's x squared units high. Well, dx represents the width of each rectangle. So this is base, no, this is height, times base. So what you're doing is adding up the area of a bunch of rectangles. And dx, when you integrate, the limit of dx goes to 0. So those rectangles get like infinitely small. But this just represents that you're adding up the area of a bunch of rectangles, and this is what we get at the end. So that's why it like disappears. It doesn't really mean anything, it just represents like an area. Probably more than you're asking, but that helps some. Okay. We'll talk about this more down the road. It's just not quite yet. Should I do 3 the other way? Do you want to go through 3 the other way? Go to 4? Yeah, what's up? Are we into ease yet? There we go. Okay. Okay. So, if you have, we can get into like, wow, okay. What do you think the big guy is? So let's talk through like scenarios of what if we made it this, what if we made it this. If we made this e the big guy, then the little guy would be 2x. What's the derivative of 2x? 2. Can I change this stuff over here into a 2 by multiplying it by a constant? Like, can I go e to the 8 times e to the 2x plus 1 times blank equals 2? I could do that. If you could, you're better than me. I couldn't. So that tells me this is a poor choice. Because the derivative of 2x is not all of that stuff, it's just 2. But what if I made this e the big guy? Now your little guy is this. What's the derivative of e to the 2x plus 1? Well, it'd be e to the 2x times 2, right? Because it's chain rule. And we have e to the 2x times 8. So can I make that adjustment? Can I make that match? I can. So you get into like, I mean, there's situations where it's even tougher than this to figure out. There's like 3 or 4 options for my big guy. And I gotta like reason through. Like if this was it, that would mean this, and that doesn't make sense. So this can't be it. Let's try this one. Okay, that would mean this happens and this happens. Okay, that kind of fits, and I can make that work. What do you mean ripping it off? Yeah, so if you want to look, yeah. I mean, it's not like really attached to the E any more than it's attached to this. They're all just being multiplied. Like really, the 8 could be out here too, you know. So what I'm saying is this E is the big. This is my little. So my little guy is e to the 2x plus 1. And that 1 is still up there in the exponent. It's coming. So what's the derivative of e to the, like if I make this my little, what's the derivative of e to the 2x plus 1? It's e to the 2x. And then what do I have to multiply by? 2. So I have e to the 2x times 8. So can I make those match? So what do I need to multiply? I need this to be a 2. It's an 8. So what do I multiply by? I'm going to put a 1/4 on the inside. But that's not really the important part. The important part is what's going to go out here. If I put a 1/4 on the inside and I want to balance it out, what's going to go on the outside? 4. Or like kind of what Ethan was saying is, I think yesterday, he's like, I'm not going to worry about that. I'm just going to turn 8 into 2 times 4. Put the 2 here and the 4 here. As long as you get the 4 out there, that's what's important. Because what's going to happen to this part anyways? It's going to go away because it's your little guy prime. So I have this 4 out here. Now my job is to integrate the big guy. Well, how do I integrate e? It's just e. So the integral of e is e. I leave this the same. 4 drops down. Sure. Should I do it again? Or should I do it like with the other way? No. What were you saying? Again or other way? Other way? I mean, it's the same. It's the same logic. Well, let's try the other one. So u. So if this is my big, I still need to know that's the big guy. So u is e to the 2x plus 1. That plus 1's down there, actually, which makes a difference. It is down there. I was looking at it wrong. Because it's like, see how it's lined up on the bottom there? Yeah. So then the derivative of u with respect to x, what's the derivative of e to the 2x? It's not in the exponent. It's not in the second exponent. It's in the, you know what I mean? There's like 2 levels. It's like this. E to the 2x plus 1. Yeah. Got it. Where are we at? Oh, okay. Questions? Why did we or how did we? Because I wanted to. Why did I want to? So I need to think through what the big guy and the little guy are. So my thought process was, if I make this e down here the big guy, that makes this up here the little guy because the big guy is like controlling the little guy, like it's the outside function. And then if I go through and work it out this way, what's the derivative of e to the 2x plus 1? Is e to the 2x times 2. And this isn't e to the 2x times 2, but I can fix it so it would be. So because that process all matches up, that's why I picked it. I don't know if that's easy to see right now, but the more we practice, the more. So then that's why I called that u. Are we good with why the derivative has a 2 there? Like e to the 2x times 2. But then I want to say e to the 2x times 8. So what do I have to do here? Multiply by 4, multiply by 4. So I end up with 4 du, and this dx is going to end up over there, equals 8 e to the 2x times dx. We good? You with me? Somewhere along the road? Yeah. So then when I go to rewrite it, what am I putting instead of e to the 2x times 8? 4 du. So 4 du. And then what am I putting instead of e to the 2x plus 1? Careful, not just u. This is u, but isn't it e to the u? Like, what is this equal? U. So doesn't it say e to the u? Let's see, that's me. This e is this e. Because the u is like that. Let me keep going, then we'll do another one. So now my integral is easy. That's the point. What's the integral of e to the u? E to the u. Like the integral of e to something to e to something. And then I replace, so I know u is this thing. So I'm just going to put it back. Should we do this one again or go to a new one? New one?
Wait, do 6.
6? Is that similar? It's e, but it's worse. It's e's and negative? Alright, here we go. So, this would be, I'm going to write it as 12e to the 3x times e to the 3x minus 5 to the negative first. So I think some of you might be starting to see, like, it's nice to have a process. Like, the u substitution is nice because it's less reasoning through things in your head. It's easy to get confused in your head. So I'm going to do this one with the u way. So I still need to think through big guy, little guy though. What's my big guy here? So if I make that my big guy, then my little guy would be what? Hold on, let's look, figure out what.
No.
Because what? This negative one is your big guy. Yes. But I think you just kind of went through. You're like, okay, wait, that what I thought at first isn't going to work. And that like happens all the time. You're like, oh, I think this is it. You kind of head down a path. You're like, crap, I'm stuck. Doesn't make sense anymore. Oh, okay, that's fine. So this is my big. This is my little, and this is what I think I can turn into my little prime. But I'm going to do u substitution to find out. So u is going to equal e to the 3x minus 5. So then du over dx, well, what's the derivative of e to the 3x? It's e to the 3x times 3. And what's the derivative of minus 5? It's just not, right? So what I have is du equals 3e to the 3x. With me? Stop me if you're not. Times dx. We good? Alright, so then I don't want 3e to the 3x. I want 12e to the 3x. So I gotta adjust that. I gotta multiply this by 4 to make that happen. So 4 du equals 12e to the 3x times dx. So then these two get replaced with 4 and du. What does this get replaced with? U. And the negative 1 is just still there. And then this is mixing up e's and ln's, because now my big guy is this negative 1. So normally it's a power, so I'm going to add 1, multiply by, oh crap, that doesn't work. Oh yeah, that's natural logs. So natural log of u, bring down the 4, plus c. And then what do I put back in place of u? Not u. E to the 3x minus 5. once I get to here, so I have taken the 12 e to the 3x dx and saying, well, no, I'm not going to write it like that anymore. I'm going to write it like 4 du. So I put 4 du to match up. So I'm replacing these two pieces because I know that's that. I can put this instead. It might make more sense if they were written next to each other, but it doesn't matter if they're written next to each other. But if I have like this, 12e to the 3x times dx is equal to 4 du. So I'm just putting 4 du here. So I could write it this way, but then when we integrate, we're just used to having the du at the back, so I'm just putting it to the back. So I'm literally just plugging in this for this. And then I integrate, and then I put the x's back in at the end. Bogowski, do you have a question? And then Kenzie, I know you're next. Yeah, I think, yeah, that's fair. And like, I think it makes it easier to identify like what to multiply by to make your adjustment. But not everyone agrees that's easier. Oh, well, yeah. That's not really an issue that we're. Okay, let's do 8. How many are at this point? How many are like on the U substitution team? Okay, so I'm just gonna raise this hand. Wait, raise your hand if you're not on the U substitution team. So if I just teach you with U substitution, is that like fair enough? Okay. You do. All right. So I still gotta figure out big guy, little guy. So like, let's just reason through it again. If I made this e my big guy, that would mean 5x was the little guy. What's the derivative of 5x? 5. Can I multiply 5 by a constant and turn it into all that stuff? I cannot. That would be a poor choice for my big guy. What about this e? If I make that my big, that makes this my little. What's the derivative of e to the 5x? E to the 5x times 5. Well, I need e to the 5x times 20. Can I make that adjustment happen? Yeah. So that makes this e my big, and up here is my little. So my little is e to the 5x, and then that minus 2 is like down on this level. I don't know why I put L, I'm sorry. So u is equal to e to the 5x minus 2. Du over dx would be e to the 5x times 5, right? So du equals 5e to the 5x times dx. So I've got my e to the 5x, I've got my dx. But I'm supposed to have a 20. Nice job. But I'm supposed to have a 20. No, I didn't do that yet. No, I didn't. It's not 5 du. That 5 is the derivative of the 5x. Because it's changing. So what do I need this number to be? It's supposed to be a 20. So I multiply by 4. So then 4 du equals 20e to the 5x times dx. So in my original problem, instead of writing 20e to the 5x times dx, so instead of this whole chunk, like both those chunks, I can put 4 du. So Devin, that's the part you were asking about, I think. Are you good there? Okay. And then instead of e to the 5x minus 2, I can put e to the u. Agree? And then this is a lot easier to integrate than this was. So what's the integral of e to the u? It's e to the u. 4 comes with it. How's that? Kansas US free, where you at? Is that good? Yeah, man. That's June number 19?